Let's go over some examples to feel more comfortable taking double integrals, iterated integrals over rectangular region. So in this example, we have evaluate the double integral of x minus 3y squared dA over region R, which is given us as the set of points in xy plane, x comma y, such that x is in between 0 to 2. Okay, my x ranges between 0 to 2, and the y is in between 1 and 2. 1 and 2. It means that we have a rectangular region. We can visualize this region by graphing that in xy plane, x-axis, y-axis. Well, x is in between 0 to 2. And y ranges between 1 and 2. So 1 and 2. So this is your y, and your x is in between 0 to 2. So if you look at this, here you get the region R, y is in between 1 and 2, and x is in between 0 and 2, the intersection between them. This is your region R. Okay, since we have fixed boundaries, it doesn't matter if you take the inner integral with respect to x, then outer integral with respect to y, or take the inner integral with respect to y, take the outer integral with respect to x. I'm going to solve both of them for you, so you see you get the exact same result. So x minus 3y squared dx dy, it means that my inner integral is with respect to x, or you can take the double integral with inner integral with respect to y, then with respect to x. So I'm going to use different colors. This is dy. This is related to the outer integral. And here you have dx, which is related to your outside integral. It means that for outside integral, we use boundary for x. For outside integral, we use boundary for y. So if we use outside boundary for y ranges between 1 and 2. 1 to 2. You also know that x is bounded between 0 to 2. For your x. If we decide to solve this integral, evaluate this integral, by taking the integral with respect to y first, it means that the inner integral has boundary 1 to 2. And the outer integral boundary has 0 to 2. Two different approaches, the exact same result. If we take the integral with respect to x first, it means that our outer integral stays the same. Just copy this down here, dy. So the outer integral and dy, the inner integral with respect to x is going to be x squared divided by 2 minus 3x y squared. X is in between 0 to 2. This is just a definite integral, all right? It means that we plug in 2, then we plug in 0, we subtract the outcomes. But note that both of these, they have x in them. So if I plug in 0, I get 0 back. I'm not really worried about this lower limit. I just plug in 2 as the upper limit, and then I take the integral with respect to 1. So here I have integral 1 to 2 dy, and if I plug in 2, I get 4 divided by 2, which is 2, minus 6 y squared. Now take the integral with respect to y, it gives you 2y minus, here you have 6 divided by 3, which is 2y cubed, 1, 2, 2. We plug in 2 for y, then we plug in 1 for y, and we do the subtraction. If I plug in 2, I get 4 minus 16 minus, and then I plug in 1, I get 2 minus 2. So this is just 0. The outcome is equal to minus 12. How about the second integral, second approach? I'm taking the integral with respect to y first. So the outer integral is going to be just stay the same, 0 to 2 dx. And here I have xy minus y cubed, y ranges between 1, 2, 2. So I'm going to plug in 2 first, then plug in 1, then do the subtraction. This is equal to 0 to 2. Okay, if I plug in 2 for my y, I get 2x minus 8 minus, and when I plug in 1, I get x minus 1. Then I have my dx. Let us simplify this first, then we take the integral with respect to x. 0 to 2, 2x minus 8 minus x plus 1 dx. So 2x minus x, it gives you x back, and negative 8 plus 1 minus 7. This integral is x squared over 2 minus 7x, and x ranges between 0 to 2. Again, I'm not really worried about my 0 because it makes the these two terms 0, so we just plug in 2. 4 divided by 2, 2 minus 14 gives us negative 12. As you can see, you get the exact same outcome, exact same result. Remember that when the boundaries are fixed, you're allowed to change the order of integration, dx dy or dy dx. Let's take a look at the graph. So your function z x minus 3y squared is this surface here. Well, as you can see, your z values over this given region are negative. So that's why on z-axis, you see you have negative values. And the region are this rectangular region is given here. So we're actually finding the volume of this surface bounded above by this region here. Let us take a look at another example. You want to evaluate the following double integral. Sine x, cosine y. dA, and your region is given as, it's a rectangular region, 0 to pi halves. Your x ranges between 0 to pi halves, and also your y. Y is bounded between 0 to pi halves. So your x boundaries and also your y boundaries. So let's take a look at the region here. X-axis, y-axis. So we are looking at the projection of the region in xy plane. So x is between 0 to pi halves, because pi halves is here, and also your y between 0 to pi halves. The intersection between them forms your region R. Well, first of all, note that sine x is multiplied by cosine y. It's not like previous example that we had addition, subtraction, connecting the terms together. Here you have multiplication and these two functions are separated from each other. There is no attachment between x and y. Okay. So the first approach is to take the integral with respect to x, then take the integral with respect to y, or you can take the integral with respect to y first, then take the integral with respect to x. I'm going to show you another method to solve these types of integrals. So let us take the integral with respect to, for example, y first, then with respect to x. So x, it is a different color, so you know that we are just having the outer integral with respect to x. So as you know, your x ranges between 0 to pi halves. We're going to copy this guy here. And the inner integral is with respect to y. So since y ranges between 0 to pi over 2, there is no difference between these. 0 to pi over 2. So let's take the inner integral with respect to y first. Remember that sine x consider as just a constant when you're taking the integral with respect to y because it's not related to y. So here we have integral 0 to pi over 2. I'm going to copy down my sine x. And here I have the integral of cosine y, which is sine y. And I know that y ranges between 0 to pi over 2. Then, after evaluating the whole thing, I'm going to take the integral with respect to x. If I plug in pi over 2, I get sine of pi over 2, which is 1. If I plug in 0, it's going to be 0. 1 minus 0 is 1. So here I have the integral of 0 to pi over 2 of sine x dx. Sine x times 1 minus 0 dx. Well, the integral of sine x is negative cosine x, and x ranges between 0 to pi over 2. If I plug in pi over 2, it's going to be 0 minus cosine of 0 is 1, negative, negative gives you positive 1. Again, you can say that, hey, I want to take the integral with respect to x first, then with respect to y, you get the exact same result. One important note here is that we can calculate these two integrals separately and multiply the outcomes. Why is that? First of all, as I mentioned, sine x, cosine y are two different functions. There is no connection between x and y. We don't have addition, we don't have subtraction connecting x and y, and the boundaries, both of the boundaries are constants. So you can write it as the integral with respect to x. So integral of sine x dx multiplied by the integral of cosine y dy. X is in between 0 and pi over 2. Y is in between 0 and pi over 2. So let me just choose the correct color. Pi over 2 for dx. Zero to pi over 2 dy. Again, you are only allowed to do that if you have fixed boundaries, and there is no connection, attachment, dependency between your x and y. So the integral of sine x is negative cosine x. X ranges between 0 to pi over 2 times. The integral of cosine y is sine y. Y ranges between 0 to pi over 2. We're just calculating each of these separately, multiplying the results. So as you know, pi over 2 makes cosine 0 minus minus 1. It is 1. And then you have the same thing here. Sine of pi over 2 is 1. 1 minus 0 is 1. 1 times 1 is equal to, you get the exact same result. There's the graph for you here. First of all, this flat plane shows r 0 to pi over 2, 0 to pi over 2, and this surface up here is sine x times cosine y. The volume between the surface and the region, rectangular region here, as be shown, is equal to 1. Another example for you. So we're going to solve the following integral, choosing the better order of integration. Take a look at this example here. Sometimes it's harder to take the integral with respect to x than with respect to y, or it's more complicated to take the integral with respect to y than with respect to x. Let me show you this example. In this example, we have the double integral of y sine xy dA, and the region given to us as 1 to 2. So these are the boundaries for our x, and the boundaries for our y is 0 to pi. 0 to pi. Well, you might say, hey, I want to take the integral with respect to x, then take the integral with respect to y, or you might say, hey, I want to take the integral with respect to y, then with respect to x. Which one is easier to evaluate? That's the question that we're trying to answer. So the setup for you, it's either taking the integral with respect to x first, then with respect to y, or you might say, hey, this is my setup. Taking the integral with respect to y first, then with respect to x. So if your outside integral is with respect to y, the boundary for y ranges between 0 to pi. And if your outside integral is in with respect to x, the outside integral has boundaries 1 to 2. Okay. So my x ranges between 1 to 2. I'm going to evaluate the inner integral first. My y ranges between 0 to pi. For this case, we're going to evaluate the integral with respect to y first. Which one is easier for us? If you take the integral with respect to x, it means that your y is a constant. It's like evaluating this integral, a sine of ax dx. So remember that you can use u sub in this case. If u is ax, du is a dx. So this integral can be written as the integral of sine u du. Sine u du. Very well. So the integral of sine u is equal to negative cosine u. Here you have And the integral 0 to pi negative cosine xy, and your x ranges between 1 to 2. Then we take the integral with respect to y. Let's plug in 2 for x. So I have a negative sign, so let's copy down this negative sign outside the integral. You get cosine of 2y minus cosine of y. Then we take this integral with respect to y. From elementary calculus, we know how to take this integral minus integral. So here you have cosine of 2y. Again, by using u solve, we get a half sine of 2y minus cosine of y is just sine y. Y ranges between 0 to pi. Remember that this negative sign stays outside, so I'll just put everything inside bracket, minus. So if I plug in y here, I get sine of 2y, which is 0, 2 pi, which is 0, minus sine of pi, which is 0, minus if I plug in 0 here again, it's going to be 0, so the outcome is equal to 0. What if your setup is like this? What if you want to take the integral with respect to y first? Well, here you have this integral. It makes it a little bit more complicated than evaluating the integral by having x first. So think about it this way. It means that we are taking the integral, inner integral of y sine of a y dy. How to evaluate this integral? You can use integration by parts. You can say that, hey, u is equal to y, dv is equal to sine ay dy, and du is dy, and the v is 1 over a, and we have a negative sign, cosine a y. Then this inner integral can be written as, so here you have 1 to 2. It makes it more complicated. So you have uv, you get negative y over your a is just x over x, and here you have cosine xy minus integral v du. Okay, I have negative 1 over x cosine xy dy. Okay, then I have to take the integral with respect to x eventually. So as you can see, it makes it more complicated than this nice and simple integral. So when you're evaluating double integrals, try to see which one makes it more easier for you to evaluate the integral. So it gets more complicated this way, by taking the integral with respect to y, then with respect to x. So as you can see, by taking the integral with respect to x, the inner integral is with respect to x, then with respect to y, we just solve this using elementary calculus techniques, and the outcome is 0. But if I take the integral with respect to y first, I have to apply integration by parts, and I have another integral here, I have a lot of x and y, they are all connected together. It makes it harder to solve this integral by taking the integral with respect to y, then with respect to